This video explains how to find electric potential at a point and the axis of a circular ring having a uniformly distributed charge. So this question is given as a numerical problem. It says that a total charge of 40 nanocoulomb. So 40 nanocoulomb is the charge. Q. 40 nanocoulomb is uniformly distributed around a ring of radius. A ring of radius 2 meters. So radius 2 meters means it is a circular ring. A ring can be rectangular or of any shape. It's a circular ring, radius 2 meters. The ring is carrying the charge. That means the ring is a line charge. Ring can be treated as a line charge of density rho L coulomb per meter carrying a charge on it. But here it's usually a good practice to give line charge density for a line charge. But here is given total charge. So we are expected to calculate rho L later, which is given by dq by dl. Differential charge of differential length. A differential length on the ring. But here total charge is given and the charge is uniformly distributed. That means charge density is constant. It is same everywhere on the ring. So we can divide total charge by total length of the ring to obtain the line charge density. If the charge was not distributed uniformly, we would have gone for differential condition. But for uniform charge, you can take total charge by total length to obtain line charge density. So if we try in this way, we are having 14 nanocoulombs of total charge distributed over a total length of the ring. Total length of the ring is the complete length of this circle, which is given by 2 pi r. That is 2 pi, the length of the ring is 2. So 2 into 2, 4 can be cancelled here. So you can have 10 nano divided by pi coulomb per meter. So this way we can find the line charge density when total charge is given for a ring. Next, a total charge is distributed around the ring of radius 2 meter with its center located at origin and lying in the plane of z equal to 0. Z equal to 0 means the ring is held perpendicular to z axis. So z axis of the coordinate system is the axis of the ring. So we can understand this statement with a diagram. Let us construct a ring here. Fine. The center of the ring, origin, the radius, can be taken as 2 meters. That is the radius. The center located. It's lying in the z equal to 0 plane. So this meets z axis at 0. So we can have a z-axis. This is the z-axis. The plane of the ring is perpendicular to z-axis. So this is z equal to 0 plane. That point is also. So we have to find electric potential at 0, 0, 5. So the 0, 0, 5 lies on z-axis. So we can designate this point as P 005, and we have to find the potential at this point due to ring. Also determine electric potential at the same point 005 if all charge of 40 nanocoulomb were to be concentrated at origin. We shall take this part of the questions later. First, we shall determine the potential at this point V. So far, in our earlier discussions, we haven't derived any relation to find electric potential due to a circular line charge. We have only discussed the methods of finding electric potential at a point due to a point charge and a straight conductor, a straight line charge, infinite line charge. We have addressed so far. So we are going to take up now the circular ring. Since circular ring is also a linear charge or a line charge, so we are going to adapt the same method here. We shall make use of differential condition here. Let us choose a small length, here. Let the length of this be equal to dl. So why we have chosen this dl? Because dl is a differential length which can be assumed as a point charge. Any charge in its differential state can be assumed as a point charge. You can take it as a point charge. dq length. So the charge on this dl can be taken as a point charge. So we have an equation for potential at a point due to a point charge, and it is given by q by 4 pi epsilon r. So if the point charge is differential charge, then it can be dq and it's going to be dv. So we can find electric potential at 005 due to charge dq, which is at a distance r. We can draw the line between point and the point charge, and we can find dv. Once you find dv, we can integrate dv along the ring to get the total potential at this point. So I would like to connect this point charge to the point. And we can take this distance as r. So this is what's up. Now the condition is, now the question is how to find r and how to find this dl. So there are two issues now. Next point, if you want to find r, we can go with this construction. Here, this line is perpendicular. So this forms a right angle triangle. See this point, which is at a height of 5, that is 005 along z-axis from the plane of the ring. So that is why this height is 5 and this line is radius. By the Pythagoras, we can find R. So R is given by square root of 5 square plus 2 square. It's a right angle triangle. 25, 4, 29. That's going to be the radius, radial distance. Next one. What is this DL? DL is a small length on a circle. So we can find that also by having a separate diagram. Here, if you go with this one, if this angle is d phi on the circle and the radius of the circle is, let us say, a, then this arc length is given by a into d phi, radius into the differential angle. In this particular problem, radius is equal to 2, so that's why it's going to be 2 d phi. So the length dl is given by 2 into d phi. 2 into d phi. But what is the use of this length? Using this length, we can find dq, because dq is the charge distributed on a differential length of dl. So dq by dl is equal to rho l, line charge density. So we may need dq for the calculation. So we are having the product of rho l and dl. Rho l is anyhow calculated already. It is, I think, 10 nano divided by pi into the dl is 2 into d phi. 2 into d phi. So finally, can have 20 into 10 power minus 9 into d phi divided by pi is our differential charge on a differential length dl. This charge can be assumed as a point charge. So let us find the potential at 0, 0, 5. The electric potential at point 0, 0, 5. So the electric potential at point 0, 0, 5 is given by the equation dV is equal to, okay, let us also mention this is the potential due to what? The electric potential at 0, 0, 5 due to differential charge, dq is given by, so any charge in its differential state can be taken as a point charge. So it is given by dV equal to dq divided by 4 pi epsilon r. So we can introduce all these terms in the equation one by one. 1 by 4 pi epsilon naught, taking free space as a medium. 1 by 4 pi epsilon naught, upon substituting for epsilon naught, we can have the value of 9 into 10 power 9. So we can replace 1 by 4 pi epsilon naught as 9 into 10 raised to 9 into dq. We have the equation here, 20 nano into d5 divided by pi. So that forms dq. And r. So r is the distance, that is root 29, I guess, because it is root of 5 square plus 2 square. 5 square is 25, 2 square is 4, totally 29. This is the r. So let us simplify here. Few terms are cancelled, right? So get 180 divided by pi root 29 into d5. That is the potential here. This is the potential at point 005 on z-axis due to the differential charge dq. d5 is the differential angle of the ring. Now to find the total potential, the total potential V at 005 is given by the integration of dV. This integration with respect to d5, single integration. So in dV, few things are constant. 180 divided by pi root 29 is constant. Only d5 has to be integrated. For a circular ring, the angle phi varies from 0 to 2 pi to define the complete circle. So this gives us a value of 2 pi. So we can find this value using the calculator. This is equal to 66.85 volts. That is the potential at point B due to the circular ring of charge. Now let us see another part of the question. Let us move on to the question. In the second part of the question, it is asked to determine electric potential at the same point if all the charge of 40 nanocoulomb were to be concentrated at origin. So the complete charge, the total charge of 40 nanocoulomb, if was completely placed at the origin, that means if all the charge is present at origin, means it is a point charge. Then what is the electric potential at the same point? So here we have to compare the electric potential at a point due to a ring and a point charge of same values. So let us proceed with the second part of the question. So in the second part, we have a charge of 40 nanocoulombs located at the origin. And what is the electric potential at this point of 005? And this is R. And we know that coordinates of the origin are 005. Then R is equal to 5 meters. So for this particular case, V is given by Q by 4 pi epsilon naught R. 1 by 4 pi epsilon naught R is 9 into 10 power 9. Q is 14 nanocoulombs divided by 5. This gives 72 volts. So look at this one now. When the same charge was distributed as a ring, it produced 66.85 volts. When it is concentrated at a point, it gives more potential of 72 volts. So the distributed charge produces less potential at a point. So that is the solution for this problem.